Hello students. So today we will continue NCERT chapter 8, which is aldehyde, ketones and carboxylic acids. So today is a theory part 5. And the sections which we will cover today is from section 8.4.5 to 8.5. This is the disclaimer. So today's learning objective, after attending this lecture, you will be able to describe the chemical reactions of aldehydes and ketones. And you will be able to explain the mechanism of few selected reactions of aldehydes and ketones. And then we will describe the uses of aldehydes and ketones. Now for your reference, I have mapped the NCERT sections that we are going to cover today. So we will be covering section 8.4.5, which is other reactions, section 8.5, which is uses of aldehydes and ketones. Then, for your better understanding of the topic, we will solve one in-text question, which is 8.4. And then we will solve in-text question 8.5. And then we will conclude with the summary. Okay, so let's begin with today's lecture. So first we are going to discuss about self-Cannizzaro reaction. Now what is the self-Cannizzaro reaction? Let us see one by one. So here we see that the reaction involves a non-analyzable aldehyde, okay, which is heated with a concentrated alkali like sodium hydroxide, which is NaOH, or potassium hydroxide, which is KOH. Okay, so here the main thing is non-analyzable. So now what is this non-analyzable aldehydes? So non-analyzable aldehydes, they are aldehydes that lack alpha hydrogens. So the absence of alpha hydrogens is crucial because it prevents the formation of enolates. Now because we don't want to form enolates, so this non-analyzable aldehydes, they lack this alpha hydrogen. Okay. So the non-analyzable aldehydes, they undergo a self-oxidation and reduction process. Now this reaction is known as disproportionation reaction. This means that the same compound is both oxidized and reduced in the reaction. Okay, so that means same compound is being oxidized as well as it is being reduced in the reaction. So such kind of reactions are known as disproportionation reaction. Okay, so you need to remember that we take non-analyzable aldehydes, which is heated in concentrated alkali, and what are non-analyzable aldehyde, which lack alpha hydrogen. So one molecule of aldehyde is reduced to form an alcohol. Okay, so what happens in this reaction, that one molecule of aldehyde, it is reduced to alcohol. Meanwhile, the another molecule of aldehyde is oxidized to form carboxylic acid salt. So one molecule is reducing to aldehyde, whereas the another molecule is oxidized to form carboxylic acid salt. Okay, so I hope you know that this oxidation involves the gain of oxygen or loss of hydrogen atoms. So this dual process of oxidation and reduction is what is the characteristic feature of Cannizzaro reaction. Okay, so this dual process, which is oxidation as well as reduction. So if you look at this particular example of self-Cannizzaro reaction, you will see there are two molecules of formaldehyde. Formaldehyde, which is a simple aldehyde. So here two molecules of formaldehyde, they are undergoing disproportionation reaction with concentrated potassium hydroxide, which is KOH. Now what is happening in this disproportionation reaction? In this reaction, one molecule of formaldehyde is being reduced to methanol, which is alcohol. Okay, if you look above, I told you that one molecule of aldehyde is reduced to alcohol. So one molecule of formaldehyde is reduced to methanol, which is an alcohol. Whereas the another molecule of formaldehyde is oxidizing to give carboxylic acid salt, which is potassium formate. Okay, so if you look at this reaction, formaldehyde is getting reduced to methanol, whereas one molecule of formaldehyde is getting oxidized to form potassium formate. Okay, which is a carboxylic acid salt. So both reduction of formaldehyde to alcohol is taking place and oxidation, that is formaldehyde to carboxylic acid. So both reduction and oxidation of same molecule is happening. So this is a kind of disproportionation reaction, and this is what happens in self-Cannizzaro reaction. Now we will talk about cross-Cannizzaro reaction. Okay, now what is this cross-Cannizzaro? Now from the word itself, cross-Cannizzaro, you can understand that what will be in this reaction. So in cross-Cannizzaro reaction, it occurs between two different non-analyzable aldehydes. In case of Cannizzaro, there were same non-analyzable aldehydes. Remember one important thing, it should be non-analyzable. That means it should lack alpha hydrogen. Okay, alpha hydrogen, the carbon which is directly connected to the carbonyl group is alpha carbon, and the hydrogen of that carbon is alpha hydrogen. Okay, so it should be a non-analyzable aldehyde. That means the aldehyde should not involve alpha hydrogens. So now this reaction requires a strong base to proceed. So more electrophilic aldehyde in the reaction undergoes oxidation. Okay, now you have two different aldehydes. Okay, so you might get confused that which one will undergo oxidation and which one will undergo reduction. So more electrophilic aldehyde undergoes oxidation. Okay, now more electrophilic means it means that the aldehyde is more likely to accept electrons, okay, which is in need of electrons very much. That is more electrophilic. And the less electrophilic aldehyde undergoes reduction. Okay, so that means it gains electrons during the reaction. So less electrophilic and more electrophilic. More electrophilic undergoes oxidation and less electrophilic undergoes reduction. Okay. So let us see this cross-Cannizzaro reaction with the help of an example. Now if you see, you have two molecules of aldehyde and both are different. Okay. And that is, you have non-analyzable aldehydes. So you have benzaldehyde, okay, and you have formaldehyde. Okay, both are non-analyzable aldehydes. Now in benzaldehyde and formaldehyde, you have to choose that which one will undergo oxidation and which one will undergo reduction. So I tell you, more electrophilic undergoes oxidation. So if you see over here, formaldehyde is more electrophilic. It is in need of electrons more than benzaldehyde. Okay, so formaldehyde being more electrophilic, it will undergo oxidation. So if you see over here, formaldehyde is getting oxidized to sodium formate after treating with concentrated NaOH. Whereas benzaldehyde, which is less electrophilic than formaldehyde, it will undergo the reduction process. So you will see that benzaldehyde is reduced to benzyl alcohol. Okay, so more electrophilic undergoes oxidation and less electrophilic undergoes reduction. So benzaldehyde is undergoing reduction and formaldehyde is undergoing oxidation. I hope it is clear what is self-Cannizzaro and what is cross-Cannizzaro. In self-Cannizzaro, you have the same molecules of aldehyde. One undergoes oxidation, whereas another undergoes reduction. Whereas in cross-Cannizzaro reaction, you have two different non-analyzable aldehydes. More electrophilic one undergoes oxidation and less electrophilic one undergoes reduction. Now continuing with this cross-Cannizzaro reaction, let us see the mechanism now for the cross-Cannizzaro. Okay, let us see how this reaction is proceeding. So what is happening in step 1? In step 1, we observe hydroxide ion, which is a negatively charged. Okay, now we have NaOH, which is a strong base. In NaOH, we have Na positive and OH minus, which is a hydroxide ion and negatively charged. Now, this negatively charged hydroxide ion, where will it attack? Obviously, it will attack the carbonyl carbon of formaldehyde. So, this OH minus ion will attack the carbonyl carbon of the formaldehyde, forming a tetrahedral intermediate. Okay, so if you look, there is a tetrahedral intermediate which is formed. Okay, the carbon is more electrophilic, means it is more likely to attract electrons. We know in formaldehyde there is carbonyl bond. Okay, so oxygen being more electronegative withdraws the shared pair of electron towards itself. So the carbon is more electrophilic in that case. So OH minus ion will attack that electrophilic carbon of the carbonyl group, and it will forward tetrahedral intermediate. Okay, so this is happening in step 1. Now moving on to step 2, it is a hydride transfer. Okay, what is this hydride transfer? This involves the movement of a hydride ion from tetrahedral intermediate to benzaldehyde and oxidized to carboxylic acid. If you look at this particular reaction, you will see that from this tetrahedral intermediate, there is a hydride transfer or hydride movement to this benzaldehyde. So if you see, oxygen has a negative charge, okay, this comes down, and this hydride of this tetrahedral intermediate goes to the benzaldehyde, and then that benzaldehyde, it will further be oxidized to carboxylic acid. So you will see HC double bond OH. Okay, so it is getting oxidized to carboxylic acid. And what is happening in step 3? In step 3, we have a proton exchange. So this step involves the transfer of proton, which is a hydrogen ion, between obtained molecules, okay, for the reduction of benzaldehyde intermediate to an alcohol along with the carboxylate ion. So if you see, you have one carboxylic acid, okay, so there will be a hydrogen, there will be a transfer of proton in this case. So if you look over here, from this carboxylic acid molecule, there is a transfer of proton to this another particular molecule. Okay, so you will get one alcohol and you will get a salt of carboxylic acid. Okay, so there is reduction of benzaldehyde intermediate to an alcohol. Okay, so this benzaldehyde is getting reduced to an alcohol. Okay, whereas this reaction you can see, which involves a proton exchange. So these are the 3 steps which is happening in the cross-Cannizzaro reaction. Okay, I hope this is clear now. Now let's move towards the electrophilic substitution reaction. Okay, so we will see in the case of aldehyde and ketones. So aromatic aldehydes and ketones can undergo electrophilic substitution on benzene ring. So what is happening in this? The carbonyl group in these compounds act as a deactivating and meta-directing group. Now we know that carbonyl compound has -I or -M effect. Okay, so they act as a deactivating and meta-directing group. This means that it withdraws the electron density from the ring and make it less reactive towards electrophiles, which electrophiles and direct any incoming electrophile to meta position. Now, if you look at this resonating structures, you will see that this carbonyl group, it withdraws the electron density from the ring. And if you see, it is with this withdrawing electron density from the ring is more pronounced at ortho and para position. If you look at this resonating structures, you will see the plus charge on the ortho and para positions. Okay, so this make it less reactive towards electrophiles. Okay, because electrophiles are already in need of electrons. So electrophiles love to attack on nucleophiles where they can get electron density. Now this CHO group, being a electron withdrawing group, withdraws the electron density and it make the ring less reactive towards electrophiles. Okay, so if any electrophile comes, it will attack at the meta position and not on the ortho and para position. Okay, so this resonating structures of benzaldehyde give you an idea about this. So what is happening? The carbonyl group, it deactivates the benzene ring towards electrophilic substitution. It reduces the ring's ability to react with electrophiles, making it less likely to participate in these reactions. Now, the carbonyl group, it withdraws the electron density from the benzene ring. So by pulling electrons away, it makes the ring less electron rich and therefore less attractive to electrophiles. So the electron density decreases more at ortho and para position than the meta position. As I told, if you look at the resonating structures, you have a positive charge more in ortho and para position. So this electron density decreases more at ortho and para position than the meta position. This means that the ortho and para position, they are less favorable for electrophilic attack compared to meta position. So if any electrophile comes to attack on this benzene ring, it preferably attack on the meta position. So the carbonyl group directs electrophiles to the meta position. This is because the meta position retains more electron density compared to ortho and para position. So if meta position has more electron density compared to ortho and para position, so it is the preferred site for the electrophilic substitution. Okay, so if you will see that if the benzaldehyde undergoes electrophilic substitution reaction, okay, you will see that the incoming group will attach on the meta position instead of ortho and the para position. So continuing with this, we will see an example. So if you see here the reaction of nitration of benzaldehyde. So this is a specific example of an electrophilic substitution reaction where a nitro group is introduced into the benzaldehyde molecule, giving meta-nitrobenzaldehyde. So if you saw this incoming NO2 group, it comes and attach at the meta position after reacting with HNO3 or H2SO4 in the temperature range 273 to 283 Kelvin. So this is an example of an electrophilic substitution reaction, that the NO2 group comes and attacks at the meta position, because at meta position there is more electron density compared to ortho and para position. Okay. So if you look at this mechanism, for the mechanism attack of electrophile, nitronium ion occurs primarily at the meta position. So if you see the electrophile, which is the nitronium ion, it occurs primarily at the meta position of the benzaldehyde ring, okay, where the electron density is relatively higher and we get a meta nitrobenzaldehyde as the product. Okay, so what is happening in this reaction? In the first step, in the mechanism is the attack of electrophile. So here, as I told, the nitronium ion, it acts as an electrophile, which is the nitronium ion, by the pi bond of the aromatic ring. In the aromatic ring, the pi bond, okay, it attacks the nitronium ion, and this forms an intermediate compound. So there is attack at the meta position, and if you can see, there is an intermediate compound which is formed. And then in the final step, this intermediate compound, it loses a proton to restore the aromaticity of the compound. If you carefully look at this mechanism, you will see that this benzene ring donates its electron density to this electrophile, which is the nitronium ion, and you get this intermediate. Okay, and after you get this intermediate, there is this proton which is getting lost, so that it could restore the ring aromaticity. Okay, so you will see that the NO2 group comes and attach at the meta position. Okay, I hope this is clear. Now moving on to the next section, we will see the uses of aldehydes and ketones. Now we studied all the way mechanism, and everything of aldehydes and ketones. Now, what is the use of aldehydes and ketones and where they are useful? Let us one by one go through it. So, aldehydes and ketones, they are used in solvents, starting materials, and reagents in the chemicals industry and in the various chemical processes and product formulations. Now, if we look at the specific examples, we will start with the formaldehyde. So, formaldehyde is the simplest aldehyde, and this compound is widely used in different applications. If we see, then formaldehyde is commonly known as formalin, okay, when in a 40% aqueous solution. So, it is widely recognized as formalin in its 40% aqueous solution. Next, one of the key uses of formaldehyde is in preserving biological specimens. Okay, so this formaldehyde, it allows the specimens to be stored for the longer periods. Next, we can see that the formaldehyde, it is also used to prepare materials like bakelite. Now, bakelite, it is a type of phenol formaldehyde resin, and additionally, it is used in making urea formaldehyde glues. Okay, and these are important in manufacturing as well as in construction. So now we will move to acetaldehyde. Acetaldehyde, which is also a type of aldehyde, is another important compound with various industrial applications. If we see, then it is used in the production of acetic acid, ethyl acetate, and vinyl acetate. So it is used in the manufacture of all these compounds. Acetaldehyde, it also plays a role in the production of polymers and certain pharmaceuticals. Okay, so let's move forward. Next, we will see about benzaldehyde. Now, benzaldehyde, its almond-like fragrance make it a popular choice in the perfumery industry. Now, because of this good fragrance which it has, it is a popular choice in perfume industry, where it is used to create pleasant scents, and additionally, it is utilized in the dye industry. Okay, now we will see towards the ketone part. So, moving on, now we see the uses of acetone and ethyl methyl ketone. Now, these are both ketones that play a significant role as industrial solvents, and they are widely used in cleaning and manufacturing processes due to their effectiveness in dissolving substances. Okay, so this all we saw the uses of different aldehydes and ketones. Now, students, let's solve the Intext question 8.4. Okay, so you try solving it with yourself and we will discuss the solution. So, if you look at the question carefully, what is this question saying? You have to arrange the following compounds in the increasing order of their reactivity in nucleophilic addition reactions. Okay, see carefully, it is nucleophilic addition reaction. So, two options are given, 1 and 2. You have to arrange this 1 and 2 according to the reactivity in nucleophilic addition reactions. Okay, and an additional hint is given to you that you need to consider steric effect and electronic effects. Okay, so I'll give you 30 seconds to think about this question and then we will discuss. Okay, let's move on to see the solution now. So first of all, we will talk about the factors that will affect the reactivity. We have to arrange it in the order of the nucleophilic addition reactions. So first we will see that what are the factors which affect this reactivity. When we'll be able to sort these factors out, then we will be able to reach to the solution. First factor is electronic effects. Now, electron donating group decreases the electrophilicity of the carbonyl carbon, okay, by reducing its partial positive charge. Now, we know that in carbonyl carbon is more electrophilic. Why? Because oxygen, being more electronegative, withdraws the electron density, which leaves a carbon electrophilic. Now, but if you add electron donating groups, now these electron donating group, they increases the electron density on the carbonyl carbon. As a result, the electrophilicity of the carbonyl carbon is reduced. Okay, so its positive charge or the electrophilicity of the carbonyl carbon is reduced. Next factor which we take into consideration is steric hindrance. Now, the bulkier groups that are around the carbonyl carbon, they can hinder the approach of nucleophiles. Now, if you imagine, if two bulky groups are present, then it will be difficult for the nucleophile to attack. Now, if it will be difficult for the nucleophile to approach the carbonyl carbon, this will make the reaction slower. Okay. Now, if we compare between aldehydes and ketones, then for the comparison between aldehydes and ketones, we will see about their structural differences and the impact on the reactivity. Now, if I talk about aldehydes have one alkyl group and one hydrogen attached to the carbonyl carbon. We have already discussed the structure of aldehyde. There is a carbonyl group, and to the carbon, one R group or alkyl, it can be alkyl or aryl, and one hydrogen is attached to the carbonyl carbon. Whereas in ketones, two alkyl groups are attached to the carbonyl carbon. So if you compare these two things, you can automatically answer that where there is electronic effect more or steric hindrances more. So the alkyl group, they increases the electron density around the carbonyl carbon. Now alkyl groups, they have the nature of donating its electron density by plus I or plus M effect. So the alkyl groups, they increases the electron density around the carbonyl carbon. Now what will happen because of this? The carbonyl carbon, it will reduce the electrophilicity of this carbonyl carbon because it is donating the electron density. So now that carbon is not so much hungry or not in so much need of electrons. So it will reduce the electrophilicity of the carbonyl carbon. Okay. So continuing with the solution, we will see that aldehydes, they are generally more reactive than ketones. Okay. Because we will see that less steric hindrance. In aldehydes, we will see that there is only one alkyl group. So if only one alkyl group is there, so there is less steric hindrance. So the incoming nucleophile can easily attack on the carbonyl carbon. Okay. Whereas the second reason is that aldehydes have they have less electron donation to the carbonyl carbon. Because in aldehydes, you will see there is only one alkyl group, so there will be less electron donation. Okay, and this makes the carbon of the carbonyl carbon more electrophilic due to less electron donation from the single alkyl group. So in case of the aldehyde, the carbonyl carbon is more hungry because there is only one alkyl group which is donating the electron density. Okay, whereas in ketones you have two alkyl groups. So you can itself think that which carbon is in more need of electrons, the aldehyde one or in ketone one. Now if you look at this figure, okay, so this is the variation in the positive inductive effect which is shown by the molecules, which is given you in the first part. If you carefully look ethanol, which is an aldehyde, they have only one CH3 group. If you see at propanol, which is an aldehyde, you have CH3 and CH2. Okay, they have this alkyl group. So ethanol and propanol, if you see, because of this presence of one alkyl group, they will have less plus I effect. Now carefully look at propanol and butanol. Propanol, which is an ketone, and butanol, which is also an ketone. There are two alkyl groups that are present, which is increasing the electron donation effect. Okay, so ethanol, there is one alkyl group CH3. In propanol, it is CH3CH2, which is an ethyl group. And in propanol and butanol, being a ketone, you will see that there are two alkyl groups which is attached to the carbonyl carbon. Now these alkyl groups, which has the nature of donating the electron density, it is reducing the electrophilicity of the carbonyl carbon. Now can you think, I have told you all the factors. Now can you arrange it in the order of their increasing reactivity towards the nucleophilic addition reaction? So if I talk about the reactivity, then you will see that ethanol is more reactive than propanol because of the less steric hindrance. Okay, so in ethanol there is one methyl group only, Whereas in propanol, there is more steric hindrance because there is this ethyl group. So an incoming nucleophile can easily attack on ethanol as compared to propanol. Okay, so ethanol will be more reactive. And if we compare aldehyde and ketone, we know aldehyde will be more reactive. But when we are comparing two aldehyde, which is ethanol and propanol, ethanol will be more reactive because in propanol there is steric hindrance because of this ethyl group. Okay, and propanol is more reactive than butanol. If you compare two different ketones, that is propanol and butanol, in propanol both sides you have one methyl group, whereas in butanol one side you have methyl group, other side you have ethyl group. So in butanol there is more steric hindrance. Okay, so the incoming nucleophile would find it difficult to attack on the carbonyl carbon. So now you can easily arrange the four given compounds in their increasing order of the reactivity. So what will be the order? Ethanol will be most reactive, okay, which is followed by propanol, then propanol, and last is butanol. Butanol is least reactive, okay, and ethanol is most reactive. So the order is based on the steric and electronic effects, okay, where smaller and less hindered molecules tend to be more reactive. Okay, so I hope this question is clear that how we arranged it. Similarly, we are going to solve for the second part. In second part also, first we will sort out the factors, okay, that what are the factors that will affect this reactivity. First we will see electronic factor. So the electron donating group reduces the partial positive charge on the carbonyl carbon. So it affects how easily a nucleophile can attack the carbonyl group. Okay, so the groups that are electron donating, they will reduce the partial positive charge. So an incoming nucleophile can attack the carbonyl carbon. And the electron withdrawing groups increases the partial positive charge on the carbonyl carbon. Now if it is increasing the partial positive charge, this makes carbon more susceptible to nucleophilic attack, enhancing their reactivity. Okay, so in electron donating groups, you see it reduces the partial positive charge on the carbonyl carbon, and in electron withdrawing group, it increases the partial positive charge on the carbonyl carbon. And if we compare the steric hindrance factor, we will see that the bulkier group hinders the access of nucleophiles to the carbonyl carbon, which will decrease the reactivity. Okay, whereas if we further talk about this, we will see this example of para-nitrobenzaldehyde. Okay, so in para-nitrobenzaldehyde, if you see, you have a nitro group. It is a substituted aromatic aldehyde in which you have a nitro group. Now, what is the nature of this nitro group? This nitro group is a strong electron withdrawing group. Now, para-nitrobenzaldehyde has a strong electron withdrawing nitro group which is attached at the para position. Now, because of the presence of this nitro group, it increases the positive charge on the carbonyl carbon of para-nitrobenzaldehyde. Okay, now this nitro group is electron withdrawing in nature. So it is withdrawing the electron density from the ring, okay, as well as from the carbonyl carbon. Okay, so it increases the positive charge on carbonyl carbon. So it makes the carbonyl carbon more susceptible to attack by nucleophiles, which are electron-rich species, because the carbonyl carbon of this particular compound is very much hungry, is in need of electrons. Okay, so incoming nucleophile, it find it easier to attack on this carbonyl carbon. So it is more susceptible to attack by nucleophiles. So it is more reactive in nucleophilic addition. Next, further we will see the next compound, which is benzaldehyde. Okay, now benzaldehyde, if you see to a ring, benzene ring, an aldehyde group is directly attached. So if you see on this, there is no substituent which is attached on the benzene ring. Okay, there is just this benzaldehyde group. So the carbonyl carbon in benzaldehyde has moderate electrophilicity. Okay, in case of para-nitrobenzaldehyde, we saw nitro group is attached. In this case, there is no substituent which is attached to this benzaldehyde. Okay, so the carbonyl carbon has moderate electrophilicity. So electrophilicity refers, now you know what is electrophilicity? it is tendency of an atom to attract the electrons. Okay, and if I talk particularly in this case, it indicates that how likely the carbonyl carbon is to participate in nucleophilic addition reactions. So if I talk about benzaldehyde, it has moderate reactivity. Okay, this means it is neither highly reactive and nor unreactive. So we will place benzaldehyde somewhere in the middle. Okay, so next compound which we'll talk about is if you take of this compound, it is para-tolualdehyde. Okay, so if you look at this particular example, you will see over there that it has a electron donating, which is a methyl group is there. Okay, a methyl group. What is the nature of this methyl group? It is an electron donating nature. So this means it is pushing the electron towards the carbonyl group, affecting the reactivity. Now, can you tell me, like, if this methyl group is pushing the electron density towards the carbonyl carbon, will that carbonyl carbon be in need of the electrons? Okay, so no, the electron donating group of the methyl, electron donating nature of the methyl group, it decreases the electrophilicity of the carbonyl carbon. Okay, so it is decreasing the electrophilicity. So the carbonyl carbon is less reactive towards the incoming nucleophile. So if I talk about, then this is less reactive than benzaldehyde. Okay, benzaldehyde, it is less reactive. Why? Because we have a CH3 group which is donating the electron density. So it is reducing the electrophilicity of the carbonyl carbon. And let's talk about the last compound, which is the fourth compound. It is acetophenone. Okay, in case of acetophenone, if we see, then plus M effect of the phenyl group decreases the electrophilicity of the carbonyl carbon. Okay, so the phenyl group, which has a positive mesomeric effect, it will decrease the electrophilicity of the carbonyl carbon. So that means the carbon is less likely to attract the nucleophiles because of the electron donating nature of the phenyl ring. So the methyl group has a positive inductive effect, which also decreases the electrophilicity of the carbonyl carbon. We have a methyl group also over here. So that methyl group is also reducing the electrophilicity of the carbonyl carbon. Okay, and this reduces the compound reactivity in nucleophilic addition reactions. So phenyl and methyl group, they are contributing to the steric hindrance, okay, which physically blocks the nucleophiles from approaching the carbonyl carbon. So what will happen as a result? The compound will be less reactive. So it is least reactive among all. Because of the electronic and steric effects, we will see that this acetophenone, it is least reactive towards all the compounds which are listed. Okay. So now can you finally arrange the order for this? So the increasing order, if we see, first is para-nitrobenzaldehyde, which is most reactive. Then it is benzaldehyde. Then we will see about para-tolualdehyde, and last is acetophenone. Okay, acetophenone is least reactive. Okay, so the order is influenced by electronic effects of the substituents on benzene ring, where we saw that the electron withdrawing group, like nitro group, it increases the reactivity. Okay, and it is making the carbon more electrophilic. So the incoming nucleophile will easily attack on this para-nitrobenzaldehyde. Okay, is it clear that how we have arranged the order? Okay. Now you have to predict the products of the following reactions. You have 4 reactions. You have to predict the order. I'm giving you 30 seconds to think and we will discuss. Okay, let's move on towards the solution. First, we will solve the A part. So the first part reaction, if you see that you have reacted cyclopentanone using hydroxylamine in acidic medium. Okay, so this OHNH2 is hydroxylamine and you have reacted cyclopentanone using hydroxylamine in acidic medium. And the product which you have obtained is an oxime. So if we look at the reaction scheme, first we will see that the carbonyl carbon of pentanone is protonated by an acid. Okay, so this cyclopentanone, you will see that it is protonated by an acid. So what will happen as a result? This will increase its electrophilicity. Okay. So now what will happen in next step? You will see that the nucleophile will come and attack on this. Okay. So what will be the nucleophile in this case? It will be hydroxylamine, because in hydroxylamine the nitrogen has its lone pair to donate. Okay. So then the nucleophilic nitrogen of hydroxylamine, it attacks the carbonyl carbon. So you will see nitrogen with its lone pair will attack on this carbonyl carbon, and further it will form a tetrahedral intermediate. Now, when this tetrahedral intermediate is formed, there is a proton transfer. Okay, so you will see that one of the proton from this nitrogen, so nitrogen has a positive charge because it is bonded by one by this ring and two hydrogen. So the nitrogen has a positive charge. So there a proton transfer will take place. So one proton will be transferred. So now this OH becomes OH2 positive. If you carefully look, this OH has become OH2 positive. Now this OH2 positive is a better leaving group. Okay, so what will happen? This OH2 will leave from here, and the lone pair of nitrogen will form a double bond. This lone pair of nitrogen will come and there will be double bond between carbon and nitrogen. So this will be C double bond N. So a double bond will be there between carbon and nitrogen. And now a nitrogen has a positive charge. So finally you will see that the deprotonation will take place and you will get a neutral molecule, which is an oxime. Okay. So the proton transfer, what happens when you get an intermediate? Now through the proton transfer, the intermediate, it rearranges and further you get finally an oxime, which is obtained as a product, final product. Okay. So this is a very classical method of converting ketones to oximes. Now for the next part. Now in this reaction, a skiff base, which is a hydrazone derivative, is formed from cyclohexanon and orthopara dinitrophenylhydrazine. And the product which you're getting in this case is 2,4 dinitrophenylhydrazone. Okay, so we will see the mechanism of this reaction, how it is happening. So here if you look towards the mechanism scheme, you will see that the lone pair of nitrogen, first step, the lone pair of the nitrogen, if you see this nitrogen has a lone pair, the lone pair of this nitrogen is attacking on the carbonyl carbon of cyclohexanon. Okay, so this proton rearrangement occurs, then resulting in the elimination of the water molecule. So if you see when this nitrogen with its lone pair attack on this cyclohexanon, okay, you get this intermediate. Okay, now in this nitrogen has a positive charge and oxygen has a negative charge. So what will happen? There will be a proton transfer. Okay, so there will be a proton transfer. So this nitrogen now has this NH and this is OH. Okay, now what will happen? Finally, you will see that when you treated an acidic medium from H plus, this OH is now OH2 plus. So now this is a better leaving group. Okay, so when this OH2 is being a better leaving group, it will leave when nitrogen with its lone pair, it will form carbon double bond nitrogen, and this OH2 will leave from here. And finally, the deprotonation will take place to give you a neutral molecule. Okay, so cyclohexanon carbon connects with the hydrazine nitrogen, which gives you C double bond N, containing the major product, which is 2,4 dinitrophenylhydrazone. Okay, so you finally get this product. Now we will see the third part for the next reaction. So this is an example of a condensation of an alpha beta unsaturated aldehyde with semicarbazide, okay, to form a semicarbazone derivative as a product. So if you look at the reaction scheme, so first what will happen in this particular reaction? So the terminal amino group of semicarbazide attacks the carbonyl carbon of the aldehyde, forming a tetrahedral intermediate. So first you will see that this carbonyl carbon is getting protonated. Okay, And then the terminal amino group, it attacks the carbonyl carbon of aldehyde and it forms a tetrahedral intermediate. Okay, after that you will see that there will be a proton transfer, okay, which stabilizes the molecule and make it easier to lose the water, because OH is a bad leaving group, but you see OH2 plus is a good leaving group. Okay, so then there will be loss of water molecule which occurs, leading to the formation of C double bond N skiff base. And if you see the final product, it is an alpha beta unsaturated semi carbazone. Okay, so when you see this proton transfer takes place, the nitrogen with its lone pair goes here, and you see you will form C double bond N. And this OH2, being a good leaving group, leaves. Okay, and then finally there will be deprotonation and you will get your neutral molecule. So the final product which you get is an alpha beta unsaturated semi carbazone. Okay. Now let's move on to the fourth part. So in this reaction is given between an aldehyde and a primary amine. Okay, specifically between benzyl acetone and ethyl amine in acidic medium, and you have get an imine derivative. So the product is N-ethyl 1-phenyl ethanamine. This is a final product which you get. Now if we look at the particular reaction, then we will go towards the mechanism. So what is happening in this reaction? First, there will be the protonation of this benzyl acetone, and after the protonation, you will see that the lone pair on the nitrogen of this primary amine, which is ethyl amine, it attacks the electrophilic carbon of it. Okay, so it forms a carbonyl amine intermediate. Okay, which is also called as hemiaminal. Okay, so finally you get an intermediate which is a hemiaminal intermediate. Then you will see there is a proton transfer. So a proton is transferred from the nitrogen to oxygen, increasing the water's leaving ability. The proton transfer takes place. Now OH2 is a better leaving group. Then you will see the molecule undergoes acid catalyzed dehydration, losing a water molecule, losing a molecule of water, which results in the formation of imine. Okay, so if you see nitrogen lone pairs come here, that is C double bond N, and water leave from here. And finally, there will be deprotonation. Okay, and you'll get a neutral molecule. Okay, so the results in the formation of an imine, and the final product which you get is N-ethyl 1-phenyl ethanamine. This is the final product which you get. Okay, I hope it is clear. So now let's conclude with the summary. So the major concepts which we have discovered today, we talk about self-Cannizzaro reaction. So this reaction involves aldehydes that do not have enolizable hydrogens, okay, and occurs in the presence of concentrated alkali. So the first is that the reaction occurs with non-enolizable aldehydes. This means that the aldehydes do not have alpha hydrogen, okay. And we see that the one molecule of aldehyde is oxidized to carboxylic acid, okay. So this is where aldehydes gain an oxygen atom, whereas we see that another molecule of one molecule is oxidized to carboxylic acid and another molecule is reduced to alcohol. Okay, so in self-Cannizzaro you have two aldehyde molecule. One is getting oxidized to carboxylic acid and other one is getting reduced to alcohol. Then we talked about cross-Cannizzaro reaction. In cross-Cannizzaro reaction, it occurs between two different non-enolizable aldehydes, where the more electrophilic aldehyde undergoes oxidation, whereas the less electrophile aldehyde undergoes reduction. Then we talked about electrophilic substitution reaction. So, in this reaction, the carbonyl group is a deactivating and meta-directing group. So, it reduces the reactivity of the aromatic ring and direct the incoming electrophile to meta position. And this, the carbonyl carbon, it decreases the electron density at ortho and para position of aromatic ring. This makes these position less reactive to electrophiles. So, Finally, we see that the incoming nucleophile comes and attach at the meta position, because at meta position there is more electron density compared to ortho and para position. Then we saw the uses of aldehydes and ketones. We talked about formaldehyde. It is used for preserving biological specimens. Okay, this is because it can effectively kill bacteria and fungi, which prevents the decay. And we saw it is used in the manufacturing of bakelite and resins. So this material are important in making plastics and adhesives. And then we talked about acetaldehyde. We saw that it is used in the production of acetic acid and acetates. Okay, so these are the components which are specially used for making vinegar and various salts. Then it has also used in pharmaceuticals. Okay, it plays a role in synthesis of certain drugs and chemicals. Then we talked about benzaldehyde, which is an aromatic aldehyde. It is used in perfumes and dye because it has a pleasant almond-like aroma or scent. And then we talked about the ketones. In ketones, we talked about we saw that they are used in industrial solvents and cleaning agents. Okay, so their ability to dissolve various substances make them valuable in manufacturing and maintenance. Thank you, student, for your attention. I hope I hope the topics which we have discussed today are clear to you. I hope you all have a good day.